In this video, instead of calculating the average atomic mass of an element, we'll actually be given the average atomic mass, and we'll be calculating the percent abundances of the two isotopes that make it up. This is more often the kind of problem you'd be asked to solve for average atomic mass, because it's really easy to go to any periodic table and look up average atomic mass for any element that's there. But it's important that we're able to take those averages from the periodic table for any element and sort of turn them around and deconstruct them to figure out what the original abundances were, or the percentages, for the isotopes in that element. So this is example problem number 1 on the sheet that you picked up in class, or that you picked up from one of your chemistry teachers. And we're going to go through number 1 just kind of as an example. All 4 of the problems on this page are very similar in terms of difficulty and setup, so if you can do one, you can pretty much do them all. So in blue here you see the average atomic mass equation that you were given in the video prior and have used already to calculate average atomic mass. And again, in this problem we're going to be given average, and we'll actually be solving for these two percentages, the percent abundance of each of the two isotopes in the problem. So in this problem it tells me right off the top the average atomic mass of gallium is 69.723 AMUs, and that it's made up of two isotopes, gallium-69 and gallium-71. And that asks us to calculate the relative abundances or percentages for the two isotopes in naturally occurring samples of gallium. So if we take the blue equation here, we're just going to fill in there the parts that we already know. For example, we're given the average atomic mass. Right at the beginning of the problem, it tells me that the average atomic mass for gallium is 69.723. You might find on various periodic tables that the averages are ever so slightly different, but more or less they're within a reason pretty much identical. It also says that there are two isotopes, gallium-69 and 71. Well, there are my two isotopes. The mass of my first isotope is 69 AMUs, so I'll go ahead and put that in. I don't know what its percent abundance as a decimal is, so as is often the case in math, we'll fill that in with a variable, and we'll call it x because it's one we're comfortable with. And so x here represents the percent abundance as a decimal of the first isotope, which is gallium-69. So the equation says that mass times percent plus the second mass times the percent. Well, my second mass is gallium-71. And so my second mass is listed as that, 71 AMUs. And I don't know my second percent abundance either. So this second percent abundance is also an unknown variable. Now, it would be pretty easy to call that one y or z or some other variable, but we know something else. We know that the percent abundances have to add up to 100% because these are the only two isotopes of gallium that there is. And so they need to add up to be 100%. Well, when we write percents as a decimal, we add them up and they don't add up to 100, they add up to 1. In other words, percent abundance written as a decimal for my first isotope and percent abundance written as a decimal for my second isotope need to add up to 1. So if my first percentage is x, my second percentage needs to be whatever's left. For example, if my first percentage was 75%, the second would have to be what's left. Well, that's 25%. And we write that as a decimal. If the first one was 75%, that would be 0.75, and the second one would be 0.25, whatever's left out of 1, or 100%. So in this case, my 2% abundances add up to, well, 1. And so if this first one is x, the second percent abundance written as a decimal will be whatever's left, 1 minus x. Okay? And we'll find out at the end that how those two numbers sort of work together. Once we've found the first percentage, we've more or less instantly found the second percentage as well. So these two abundances, x and 1 minus x, when we put those together, will add up to 100%, or written as a decimal, will add up to 1. And that's our equation. From there, we just solve for x, which isn't as hard as it might look in this equation. I'll walk you through it and show you how we get there. So first thing to do, we want to get x by itself eventually, but we're going to have to begin by distributing out 71 AMUs. So I'm just going to rewrite my equation again and just do that first part. So 69.723 AMUs, still on the left side of my equation. On the right, I really can't do much here yet, so 69 AMUs times x. And then here's where we'll do the distributing. 71 AMUs times 1 is 71 AMU. And, AMU. And then 71 AMU times a negative x means we get minus 71 AMU x. Right? And so it's distributing to a negative x. We end up with a subtraction or a negative 71 AMUX. So in this case, then we want to get like terms together. So I'm going to group my x's. I've got 69 AMUX and I've got negative or minus 71 AMUX. I'm going to put those together. I'm also going to get rid of my AMUs and bring that over to the other side. And so the first thing I'll do here is subtract from both sides 71 AMUs on the left and on the right, and on the left the same. So subtract 71 AMUs here. And that will make this then cancel out and disappear, essentially. When I subtract over here 69.723 minus 71, and put that in your calculator, you're going to get a negative answer, obviously, because you're subtracting a larger number. And you'll get specifically here negative 1.277 AMUs. Now we're not too wrapped up in rounding in this particular example, so we're kind of breaking some of the rounding rules for now. But to get us through this problem and kind of introduce you to the calculation anyway, we're going to be okay with that for today. On the other side of the equation, we've got 69 AMUX and negative 71 AMUX, or essentially 69 minus 71, which gives me negative 2 AMUX. Now, the AMUs are about to cancel out, so they've been kind of just hanging around for this whole problem anyhow. But to get the x by itself, we're going to divide both sides by negative 2 AMU. So I'll do that over here, and again on the right side, divide by negative 2 AMU. And on the right, the negative 2 AMU will cancel, and leave me with just my x. On the right side, the AMUs will cancel, which is nice. And it'll leave me with simply this, negative 1.277 divided by negative 2. Well, even the negatives can cancel out essentially, because negative divided by negative makes a positive. So more or less these kind of become positive by canceling each other out. And then we'll go to our calculator and do the final calculation here. So bring up a calculator. I've got 1.277 divided by 2. And my answer comes out to be 0.6385. All right. So back to my spread, my slide here. 0.6385 is my value for x. X 0.6385. Now, often in math problems, we get to the end, we solve for x and think, oh, we're done, we've got x. But we need to know what that x was. So you need to go back and remember, what did we assign x to be the variable for? And way back up here at the top, x is the percent abundance, written as a decimal, of my first isotope, which was gallium-69. Now, written as a decimal, 0.6385, is still representing a percentage. And so if you kind of imagine moving in reverse, when we turn percentages into decimals, we move our decimal point 2 places to the left. To turn that decimal now back into a percentage again, we need to move the decimal point just 2 places rather back to the right. So this becomes 63.85%. And remember, it was with the first isotope, so X was with my gallium-69. So 63.85% is gallium-69. And the rest, or what's left out of 100%, is my other isotope. So you can subtract 63.85% from 100, and you'll get your other percentage abundance for the second isotope. And if I subtract 63.85 from 100, I get 36.15%. And that's the gallium-71 isotope's percent abundance. So in this particular problem, we've got more or most of the galliums of the known universe galliums. Most of them have a mass of 69 AMUs, and then some have a mass of 71 AMUs. That kind of makes sense. If you think back to the original mass, the average atomic mass was 69.723, so it's a little bit closer to 69 anyway, and so more of the gallium atoms in the universe are known to be gallium-69, and fewer are the heavier mass, like gallium-71. You can think about this more or less like a pie chart. If we think about breaking up a pie chart, 63% to 36%, that's kind of what we end up with here. So in these problems, you'll only be finding the percent abundance for 2 isotopes of a particular element, and we'll select out some elements where there are just 2 stable isotopes known, and we'll calculate those from there. So that's example number 1. Every problem on this page sets up just the same. You'll plug in the average atomic mass, as we did, 69.723, and you'll plug in the 2 masses for the isotopes that you're given in the problem. Here, we were given masses of 69 AMUs and 71 AMUs. And then you just set it up and solve for x, and then at the very end, solve for 1 minus x, and you've got your second percentage as well. Give those a try, and we'll take questions on them when we're together in small group next. See you then. Thanks.